Well, good day to you. I hope things are going well with you. Um, this is an example that deals with a confidence interval for population mean when sigma is known. When I say sigma, I mean the population standard deviation. Okay, and so here in this problem, we are given some data, and we want to say something about a population mean. Well, the source of data here is the U.S. Bureau of Labor Statistics, and it collects information on the ages of people in the civilian labor force and publishes the results in this journal called Employment and Earnings. Now, 50 people in the civilian labor force are randomly selected, and their age, or their average age, I should say, is 36.4. And we're going to assume that the population standard deviation of the ages is 12.1. What we want to do first is find a 95% confidence interval for the mean, which I'm calling mu here. Mu is the parameter I want to estimate with a confidence interval, and that is the average age, or the mean age, of all people in the civilian labor force. I know that the average age of people in the sample is 36.4, but what about all people in the civilian labor force? I want to use this information, this sample information, to infer or draw conclusions about this parameter that is unknown. So I'm using a confidence interval to get at that. This right here is my parameter, what I'll call the parameter of interest. Okay. And what we ultimately want to do is we want to estimate mu with a confidence interval, which I'll abbreviate. Okay. The trick is, which confidence interval do I use? Up to this point, you've probably seen 3 or so, or maybe you've seen 3 or so. X bar plus or minus z sub alpha over 2 times sigma over root n. Should I use that? Or x bar plus or minus z sub alpha over 2 times s over the square root of n. Should I use that? Or should I use x bar plus or minus t sub alpha over 2 times s over root n? Which of these 3 do I want to use? Well, which one fits the problem? In this problem, I've assumed knowledge of the population standard deviation. In other words, I'm assuming that sigma is 12.1. Now, this is actually not a reasonable assumption in practice, but for pedagogical purposes, we'll go with this problem here. But I've assumed sigma is 12.1, and the only formula here that uses sigma in it is this one. And if you recall in your textbook, you can use this formula if the underlying population from which you sample is normal, or if the sample size is large enough, or in other words, if n is, for us, greater than 30. And that is the case here because we have a sample size of 50. 50 people are randomly selected. Okay, so this is our formula we're going to use for our confidence interval. So what we need are just really 4 pieces, and the arithmetic is really pretty straightforward. The first piece here is from the sample. We see that the sample mean is 36.4. Okay, that's the sample mean. And we also know that 12.1, that is given. We also know that n is a sample size, n is 50. And the other trick here is getting at z sub alpha over 2. That may take a little more work. But z sub alpha over 2, okay, what is that? Well, what's alpha? Well, if we have a 95% confidence interval, then alpha is what we need to add to 95 to get to 100. If you recall, 95%, this says my confidence interval will capture the parameter 95% of the time in repeated sampling. So that means 5% of the time, or with alpha percent of the time, it will not capture the parameter that I'm trying to estimate. So you desire this number to be big and the alpha to be small, but there is a trade-off between alpha being small and the width of the interval not really being of a usable length. Okay, back to z sub alpha over 2. So I'm looking at z sub 0.05 divided by 2. That's z sub 0.025. Okay, so what is that? Well, I'm going to draw a picture here. This is just a percentile on the standard normal distribution. Here I'm looking at z sub 0.025 is the particular value of z such that the area under the curve to the right of this value is 0.025. Well, that means the area under the curve to the left of this value is 0.975. So what I have to do here is I'm going to look on table C of the textbook and see which z-score has an area to the left of that value of 0.975, or as close as I can get to it. So here I've got my table, trusty table C, and in table C here I'm looking at 0.9, let's see, I'm looking for 0.975 in the middle of the chart for an area, and this is, I got it, I nailed it right on. The z-score that corresponds to 0.975 is 1.96. Okay, 1.96. So z sub 0.025 is 1.96. All right, now I've got my four pieces, this piece, this piece, this piece, and this piece, that I need to compute the confidence interval. All right, so moving forward here, x bar plus or minus z sub alpha over 2 times sigma over the square root of n. What does that look like? Well, that is 36.4 plus or minus 1.96 times 12.1 over the square root of 50. Okay, so I keep moving here. 36.4 plus or minus. What I've got here is 1.96 times this ratio reduces to 1.71, and this is the standard error of x bar. You recall that from the sampling distribution of x bar theory, the standard error of x bar, or the standard deviation of x bar. Okay, so moving on here, we've got 36.4 plus or minus 1.96 times 1.71, and that is 3.35. And it turns out that this quantity is an important one. This is called the margin of error. And basically what it says is, assuming my confidence interval captured the parameter that I'm trying to estimate, if that assumption is true, then this number 3.35 is the furthest my point estimate. Recall the point estimate here is 36.4, but this number 3.35 is the furthest my point estimate is from the true population mean there. So that's how we think of the margin of error. But if I've got 36.4 plus or minus 3.35, that gives me a lower bound of 33.05, comma 39.75. And so what we would say, if we were to interpret this statement, we would write something out like this, that we are 95% confident that mu is between 33.05 years and 39.75 years. Now, we could be wrong. 5% of the time, this formula is wrong. But 95% of the time, it's right, meaning the true parameter we're trying to estimate, mu here, is going to be in that interval. Okay. Well, what if we just did a 90% confidence interval for mu using the same sample information as before? Now, I'm not going to go through the whole problem, but it turns out if you crank through it, you'll get this value here, 33.59, comma 39.21. Okay, and so what we see here is this interval is actually a little more narrow than this interval. Okay, well, one reason is it turns out that the number we would plug in for z sub alpha over 2 would actually be a little bit smaller than 1.96, which makes the interval, and mathematically makes the interval more narrow. Another reason is if we relax our confidence level from 95 to 90%, then we can be more precise about where we think mu lies. We can make our interval more narrow. Now, when that's at a cost, though, we're making our guess about where mu is more precise. That window, that interval, is tighter than it is here, but we're assuming a 10% risk of being wrong in this context versus in number 1, where we just assumed a 5% chance of being wrong. So there's a trade-off between the width of the interval and the confidence level. The larger the confidence level, the larger the interval. The smaller the confidence level, the smaller the interval. You just need to be mindful of, you want a good confidence level. Usually 90% is about as low as people go. You usually see 90, 95, and 99%. But you want your confidence interval to also be of a usable width. So you need to be mindful of that when you choose your confidence level.